Okay, so let's start at where. Okay, so let's continue about the holomorphic universal covering space. Okay, so let's start with this one. So. Okay, so let me just quickly recall some concept. Okay, so okay, so recall that a deck transformation or covering transformation. Okay. Of a covering space gamma from x hat to x is a homomorphism phi from x hat to this x hat. Okay. So and such that such that gamma composed with this phi is equal to gamma. Okay, so and also and the group of deck transformations is denoted by so this is just recall some concepts from the covering space here, and then okay, so if the above is a Riemann surface covering, covering then the holomorphic lifting theorem okay, so here is close let me write down the name of the theorem. Okay, so theorem 5.1.3. You can refer back to the holomorphic lifting theorem. Okay, so implies that okay, so deck of this gamma is a subgroup of automorphism group of x hat. Okay, so when I say so here Okay, so here, this group is exactly the group of automorphism of X, where by saying automorphism, it means that it's a biholomorphism of a Riemann surface onto itself. Yeah, so it's called an automorphism. Okay, so, sorry, yeah, okay. Yeah, so this is an automorphism. So, okay. Okay, so, okay. Okay, so moreover, the holomorphic lifting theorem and theorem 10.4.5 holomorphic lifting theorem and theorem 10.4.5 okay, so together give the following. Okay, give the following. Okay, so maybe I'll stay here. Okay, so yeah, let me state the theorem. Yeah, so okay, so here we have the name as theorem 5.1.6. Okay, so here that gamma from x hat to x. Okay, sorry, x tilde to x be the homomorphic with the covering space of a Riemann surface X. Homomorphic universal covering space of covering space of a Riemann surface X. Okay. And then, okay, so then, okay, so this gamma, okay, which is be defined as the declination group of the gamma is a subgroup of the automorphism group of this X tilde. Okay. That X properly discontinuously and freely. Okay, so discontinuously and freely on X tilde. And okay, freely on this X tilde. Okay. So and then and okay, and there is a unique So here is a unique holomorphic structure. On this execute a quotient dot by this gamma relation by gamma, so giving rise to a commutative diagram to a commutative diagram. Okay, so for the diagram, so execute here we have the projection of gamma and this x, and then we have this as the quotient map of this executor, and then that's the corresponding quotient space by this relation of this gamma, and then this is the isomorphism. Sorry, it's a biholomorphism. Yeah, so this is a biholomorphism. Yeah, so it is a biholomorphism. Okay, so in which this quotient by this quotient map is holomorphic. Okay, so holomorphic map covering map. Okay, so and the map from the quotient space to X is a biholomorphism. Okay, so let me try to prove the let me try to prove this and the second one. Okay, so let me try to prove that. So so let me try to prove this statement. So I'll call this star. Okay, so if the above is a Riemann surface covering, then the holomorphic lifting theorem implies that the Dirac transformation is a subgroup of automorphism group of this X hat. I want to use the other part of the board. So let me move this around here. Sorry, I didn't. Okay. All right. Okay, so this nice little cat here. Okay. All right. Sorry, I have to erase these. All right, so so what we want to prove is that so we want to say that if E is about is a Riemann surface covering. Okay, so then the holomorphic linking theorem implies that the Dirac transformation group of this gamma is a subgroup of the automorphism group. So it's about the Riemann surface covering. Okay. If the above is a Riemann surface covering. Okay, I see. Okay. If the above is a Riemann surface. Okay. Yeah. So here so our setup is that so current here we let this gamma from let's see x hat to x be a Riemann surface covering. Okay, so Riemann surface covering of this x. Wait. Okay, let me think. Okay, so well, then gamma is okay. Okay. Wait. Okay. Okay. So so we are saying that so we know that this x so by the setup, this x is a complex one manifold. Okay, so this is a complex one manifold. Okay, so this x is a complex one manifold, and then so this x hat by definition is a Riemann surface, right? Yeah, it's a Riemann surface. So therefore, so it's a connected complex one. Yeah, connected. Yeah, so it's a Riemann surface, which is a connected complex one. Yeah, one variable. Okay, so so let's see. Okay, and then we also have that this so here, and then we also have that this phi is a homomorphism, right? So from such that this gamma composes phi is equal to gamma. Okay, so and so that phi from x hat to x hat be the whole so be a homeomorphism such that we have the Okay. Okay, so let's see. Okay, so holomorphic lifting theorem. Okay, so the holomorphic lifting theorem says that if you have gamma from x to x, we are covering real surface or real surface x. That wait, shoot. Okay. Sorry, I think this x has to be a Riemann surface. Okay. Yeah, because yeah. Okay. Okay, so now what we have, okay, so now what we have is that, okay, so the holomorphic lifting theorem says if this gamma from x hat to x is a covariant surface of a Riemann surface x, and then that this phi from y to x be a holomorphic mapping of a Riemann surface y to x. Oh, okay. So, okay. Okay, so we are holomorphic mapping of a Riemann surface y to x. Okay, covariant is holomorphic. That is a holomorphic covariant space. The holomorphic lifting theorem. Yeah, so basically our goal is to show that, okay, so yeah, we want to show that this stack transformation group is actually a subgroup of this automotive group. So basically the stack transformation group is, so for each element, it must be a biholomorphism, right? So this is what we're trying to show here. And then, so why is a biholomorphism? So, if it's a lifting, oh, okay. Ah. Wait. If it's a lifting of, okay, so if it's a lifting of phi, wait, you have to be a holomorphic mapping, right? Yeah, so you have to be a holomorphic mapping. So, but it is then phi hat is holomorphic. Okay. Okay. Yeah. So let's see. So here, we have this x hat. So we have a homeomorphism. Okay. Yeah. That's the issue here. We are lifting of phi. We are lifting. Wait. It's not a holomorphic mapping. Then phi hat is holomorphic. Wait. Phi hat is holomorphic. What's mean by lifting? This is a lifting. Yes. which one is the lifting? Okay. Okay, so we are composed with this one. Okay, so phi composed with gamma equal to gamma. Oh, okay. If you have this x hat here, and then this is gamma here, and then this is also x here, and then you have x hat here, and then let's see, it is like a 5 here. Okay, so we know that this is a given that so we know that this gamma, so we know that this gamma from this x hat to x is it basically is holomorphic, right? It's holomorphic. It's local. Yeah. Okay, yeah, it's holomorphic. And then wait, okay, so and then okay, and then okay, so and then okay, so this is a so this is a holomorphic mapping. Okay, so it's a holomorphic mapping from this one Riemann surface to another Riemann surface. Okay, so and then this is also a co-Riemann surface of this Riemann surface x hat to this Riemann surface x. Okay. Yeah, let me remind you of what is the sorry, I didn't state what is the holomorphic lifting theorem. So holomorphic lifting theorem says, okay, so let me remind you of what is the holomorphic lifting theorem. So holomorphic lifting theorem. So yeah, okay, so here we let gamma from x hat to this x be a covering Riemann surface. Of a Riemann surface x. And then that this phi from y to x be a holomorphic mapping of a Riemann surface y to x. And then, okay, I'll just take part A of this theorem. Okay, so part A says